Hey there, my fellow intellectuals. Kyle here with another video. And today we're going to do something that I think has been overdue for quite some time now, and that is we're going to cover my first author paper in graduate school. It's right here. I printed it out. But this was published back in August 2022. And I thought with this video, what I would try and do is do a bit of like an author summary, just sort of covering what went into this paper, what was the problem I tried to solve, how did I try and solve it, the results that came out of it, and future directions, and just give you an idea of, all of that good stuff. So without further ado, let's just get right into it, shall we? So let's just go ahead and switch the camera angle. And yes, here it is, black hole mass measurements of early type galaxies, NGC 1380 and NGC 6861 through ALMA and HSC observations and gas dynamical modeling. Whew, what a title. I wanted it to be fairly descriptive of what I did, but I think this does tell you exactly what I did. I measured the black hole masses of these two galaxies, NGC 1380 and NGC 6861. And as I've talked about in the past, my research uses observations from the Atacama Large Millimeter Submillimeter Array, also known as ALMA, and I also use data from the Hubble Space Telescope. So, big picture overview. Let me just give you the abstract because this tells you sort of the fundamental things that were found. So for the galaxy NGC 1380, I figured out that the black hole mass in this galaxy is about 150 million times the mass of the sun. The uncertainty is about 40%. A lot of the work went into figuring out sort of what is the overall uncertainty in this measurement. And then for NGC 6861, for certain reasons that we'll get into, the mass of the black hole could not be tightly constrained. It was, anywhere between 1 and 3 billion times the mass of the sun. But this does actually encompass a prior measurement of the black hole mass in this galaxy. And so I guess overall that's a good thing that there is some agreement there. And so the introduction kind of just tells you a little bit about, why black hole mass measurements are important, how there are different scaling relations between the mass of the supermassive black hole and properties, large-scale properties of the galaxy that it lives in. So for some reason, there seems to be this ability for galaxies and their supermassive black holes to talk to each other on big scales. But the thing is that the supermassive black holes, they're gravitational influences of radii, not their Schwarzschild radii or their event horizon radii, but there's the region of space where they're sort of the dominant contributor to the gravity of that area. It's not that large compared to the entire galaxy. And so for some reason, they're still able to, the black hole masses are somehow still connected to these larger scale properties that are measured farther out from where the black holes are typically the dominant contributor. So again, like I said, there's that radius of influence. This is how you sort of calculate that. And sigma star is just the sort of the random motion of stars at the central part of the galaxy. So that's basically the introduction. So then section 2, I get into the data that was used. So like I said, we used data from the Hubble Space Telescope and the Atacama Large Millimeter Array. So you can see here that at the center of these galaxies, this is just at the very center, you see that there is this nice circumnuclear dust disk in both galaxies. And you can also see that so this is from HST, the Hubble Space Telescope, but then on the right side, you can also see that there is CO gas from the Atacama Large Millimeter Array. So this is in the radio wavelengths, and these are in the optical wavelengths here. So we can see that the gas and the dust are occupying sort of the same region of space. And as you can already see here in NGC 6861, there is sort of this hole in the distribution of CO. That is, there is just no CO gas there. There's also like sort of a corresponding hole in the dust. I'll just give you a spoiler right now. I don't know why that is the case. Not entirely sure how these things form. But this hole was pretty much one of the biggest reasons why we couldn't get a good constraint on the supermassive black hole in NGC 6861, because we just don't have dynamical information in this area. Okay, so moving on to section 3. This is an image of the color maps. So essentially how you create this is that you take the image of this disk in 2 different wavelength filters. So this is with the Hubble Space Telescope. So we used, from wide field camera 3, we used f110 wide. So that's 110, that's 1.1 microns. and this is 1.6 microns. So this is in the near infrared regime. And the reason we use the near infrared is because dust attenuation is reduced at longer wavelengths. So dust typically will scatter light at wavelengths that are comparable to the sizes of the dust grains. And so it scatters light strongly in like the optical and like the ultraviolet, but the dust attenuation or the scattering is much reduced at longer like infrared wavelengths. But that doesn't mean it's zero. So you can clearly see on the near side of these disks, you can see that this part is what we would call reddened, as in the differences in the light is large in this area, as in there is more just dust, or dust is strongly affecting this area more so than in the lighter areas. But there's also, I don't want to get too technical, but there are actually certain configurations where this doesn't entirely tell the whole story. And I'm already going to try and stop myself from getting in too deep. But if you want to learn more about the dust corrections and how I use these images to sort of quantify how much sort of light was lost in this area, then, read on, I say. Figure 4 is a very important plot in this paper because this is effectively the plot that helped me create these extinction corrected profiles and coming up with the estimates for the blue dots. So long story short, what it does is that essentially for a given color or color excess, more specifically that you see in the color map, I effectively can translate that value to an estimated amount of extinction in the V band. Now this is based from that Riek and Lebowski paper from 1985, but also because of the assumption that the extinction in V is proportional to the extinction in H or F160 wide, you can work out how much extinction of the H band, so this is again the brightness of the central part of the galaxy along the major axis in the F160 wide filter, you can estimate just, where do these red dots end up if you assume there's this amount of color that you see in this plot here. So that is essentially the big, I guess, realization I had. I would say this is my quote-unquote greatest contribution, in the sense that it's a very simple way of doing this color correction estimate. I know it's not very rigorous. There's way more rigorous methods of doing it, but for some reason, it just hit me one day. I was like, wait a minute. I have these major axis corrected profiles. I have a color map where I can physically measure along the major axis, the long axis of this disk, how much color there is. Why can't I just use that to figure out, how much extinction there must be in the H band, and then just see where do those points line up in the plot. So that was sort of the big key realization for me in this paper, sort of figuring out, I can make an estimate. It might not be the most rigorous way of doing it, but it's a way of doing it, and it's more honestly than what, not to throw too much shade, but it's more than what other works have gone into. So I thought it was fairly, a decently qualitatively. Let me try again. So I don't know, it may not have been the most rigorous approach, but it was fairly quick to do and provided some sort of way of figuring out just how much dust there had to be in these systems. There are more advanced methods of doing it that are way more complicated, use way more complicated physics than what I tried here, but they're very computationally expensive. And as I go to show, I think what the results will show is that no matter how good your correction will be, there's always going to be a sort of a fundamental uncertainty associated with how much, your estimate of how much stars there have to be. So also, I didn't expand upon this earlier, but effectively how I used this curve was that I effectively inverted this relationship. So you can see that this is color or color excess as a function of extinction, right? So the color or the color excess can be gotten from this plot here, or this image, but I want the inverse. I want to be able to say, for a given, delta J minus H, I want a specific extinction value in the V and correspondingly the H or the F160 wide filter. And so what I did was I effectively just fitted this curve up to this point here, because it's not going to be one-to-one anymore after you fit up to this point, as in there's going to be more than one value of extinction for a given color excess. And so I effectively inverted this relationship up to this point. I found a third degree polynomial that fitted this, and then I inverted it to get the, essentially imagine putting AV on the y-axis and delta j minus h on the x-axis. So effectively, for every point along the major axis where you have a measured delta j minus h, you can associate that with a given AV and a given AH. Now you can also try and do this with the right-hand side of the curve, which I did try, but effectively what you do here is that, or what you get, I should say, rather, is that the blue dots, the extinction corrected points, are just completely kind of off the chart, so to speak. It's not literally off the chart, but it's just unphysically just different. So these blue points are just scaled up much more more highly than what where they are right now. So effectively, yeah, I tried it on the high side, did not really work, so we used the low extinction side to make that correction. So the details of the intricate nature of how I made these models is in this section right here. I'm going to move down here to figure 5, which just shows the different enclosed mass profiles of the stars for NGC 1380. And you can see that as we go to large radii towards the edge of the dust disk, the mass is well constrained. All the models tend to agree with how much mass there is at large radii. But as you get closer to the resolution limit of the telescope, that's where they start to disagree. And importantly, that's where the black hole has the most influence on the gravity. And so if you don't really know how much stellar mass you have in this area, then the black hole mass will also be fairly uncertain as well. Section 4 goes into just the modeling method that I developed in Python and what it actually does. So like I said, we have these rotating disks of gas at the center of the galaxy, and my Python code effectively models the projected line of sight velocities that you see. So if you measure how fast the gas is moving at certain points on the disk, my model effectively tries to account for that. What we have down here is a plot of the isophotes. So isophotes are just the ellipses of constant brightness between the model and the galaxy. So the black is the actual HST F160Y, that's the H-band near-infrared light, and then the red is my model's attempt to fit that, fit those isophotes. And you can see it does a fairly good job at large radii, but of course the ellipse represents where the dust sort of is. You can see that there's a bit of a disagreement between the model and the data as you get deeper and deeper into the dust. And you can see it's actually even more profound in NGC 6861. You can see this really just this non-elliptical nature of the observed galaxy isophotes as you get into the center. So again, accounting for dust and how it is affecting the amount of starlight that you see. It's very important. So this is the lone equation in my paper, just saying the different contributors to the gravitational potential and the resultant circular velocity you would expect at different radii. So this is the black hole, of course. This is from the stars. So MGE stands for multi-Gaussian expansion. That is essentially just fitting a lot of Gaussian functions to these galaxy images. These are the components of those Gaussians in this table. And then lastly, we actually incorporate the mass of the gas disk itself, just for completeness. I mean, the gas does have its own mass, though it does tend to be quite less massive than both the stars and the black hole. And usually the inclusion or the exclusion of it is not that vital, as I will show in the tests. Figure 7 is a nice plot showing the rotation curve, or what we call the position velocity diagram, along the major axis of these disks. So imagine, again, you have these rotating disks, and then you have alongside, like you just think of it as like an ellipse. And if you take a measure of the velocities along the long side of that ellipse, you'll see that rotating disks will have essentially equal and opposite velocities on both sides of the center. So this is at sort of the center, 0 arc seconds. And you can see that the velocities in NGC 1380 are about 300 kilometers per second. You can sort of see this nice sort of Keplerian-like rise. It's very, very faint. But essentially, if you imagine you have a object in orbit around like a supermassive black hole, what you'd expect is that you'd expect that near the black hole, you would see this really dramatic increase in velocity, as long as you have gas there or some tracer like stars, something to tell you that there's, an object in orbit around a black hole. Again, this is kind of why for 6861, the hole is a a really big limiting factor, because there is no dynamical information. There are no gas clouds rotating in this region, and so we're limited to dynamical information that is much farther out. So, example, in 6861, you don't see any sort of indication of a rising velocity, and there's just really no gas whatsoever inwards of like 1 arc second on both sides of the disk. Okay, so we go into the model optimization section. I built this noise model to calculate chi-squared. So chi-squared is sort of a measure of goodness of fit between models and data, just telling you how good is my model fitting the data. Put a lot of work into this. Won't get into it here, but if you're interested, you can read this section. And oh yes, the plots that are probably my favorite to look at, the moment maps of the two galaxies or the two circumnuclear disks. So we have the data and the model and the residual between them. And so this is just the surface brightness of the CO gas. This is the velocity of the line of sight velocities of different points on this disk. So you have a red shifted side. Of course, that's the side where the gas is sort of rotating away from you. And then the blue shifted side is the side of the disk that's rotating towards us here at Earth. And so you have red and blue shifted velocities, and then also you have this sort of random motion of velocities in the gas, represented by this sigma line of sight term here. Same goes for NGC 6861. The yellow ellipses and annuli, they represent where the data or where the fit occurred. So essentially we're only fitting to pixels in these elliptical regions right here, because we want to be able to constrain the fit to regions where the black hole is going to be, sort of a dominant or not a totally subdominant contributor to the gravitational potential, because at large radii out here, outside of these ellipses, it really is the mass of the stars that's dominating the gravitational potential. So you want to fit fairly close to the black hole. So, you're fitting to pixels that, have information on, gas that is sort of in an area where the black hole has some effect on the gravity. This table just shows all the different results so these are just the model free parameters right here. Of course, the one that we care about sort of the most is the mass of the supermassive black hole. So you can see on the small end, we're getting about 100 million times the mass of the sun for NGC 1380, and on the high end, about 185 million times the mass of the sun. And the model that had the best overall fit was this one right here, measured by the lowest chi-squared value. And it had a black hole mass of about 150 million, 147 million times the mass of the sun. And if we look at NGC 6861, again, we sort of have a very large range, like I said, because of that hole in the distribution. Right? This hole is just really a huge limiting factor in terms of how tightly we constrain the supermassive black hole's mass. And we get this sort of large range between 1 and 3 times 10 to the 9, or 1 to 3 billion times the mass of the sun. So we have the comparison between data and model line profiles. One thing before I continue, and this is something that I probably should have done earlier, but I'll do it now, is effectively explain how the ALMA data, what kind of form does it come in. So I'm going to put an animation here so you guys can sort of visualize what's happening, but effectively, ALMA data comes in the form of data cubes. Now, a data cube is effectively a stack of images taken at different frequencies over the same spatial region, okay? And so when you have like a rotating disk, you're going to see the effect of the Doppler shift, effectively, because this gas is emitting emission at a specific wavelength in its own rest frame. But because of the rotation of the disk, it will have, by the time it reaches us here on Earth, it will have a spread in those frequencies or wavelengths because of the Doppler shifted motions. Because again, you have this relative motion of the disk relative to our line of sight. And so with data cubes, what you can do is you can image different parts of the disk at different frequencies, which correspond to different velocities. And so my models, what they're effectively doing is that they are creating these images, or they're creating, data cubes that take in these parameters like black hole mass and parameters related to disk orientation to effectively recreate the observed data. And that's how, we're doing the fit. We're comparing our models to the data and just figuring out what's the best set of parameters that give us, the best recreated observed data set. Now that you understand that, let's talk about figure number 10. So figure number 10 shows what are known as line profile extractions. Now, if you think about a data cube, the cube part, right, you have a stack of images, right? So you have different images stacked on each other like this. But at each separate pixel, you have a spectrum. You have what is known as the line profile, as in the intensity of that line, the brightness of that line at different frequencies and wavelengths, okay? And so what we have here is we have how bright, or the relative flux of those lines at different velocities relative to the galaxy's velocity of its center of mass. And you can extract at different pixels just, what the shape of that line profile is. And you can see that they become quite, asymmetric. We assume that they're inherently Gaussian, but because of sort of the broadening of these lines due to like gas turbulence, for example, that they become highly asymmetric. And there's also, I should have mentioned before, that there's also telescope effects from just the finite resolution of the telescope that limit just how well we can resolve these lines. But you can see that the models in blue are doing a fairly good job of fitting the overall structure and shape of the data within the error bars of the measurement. So overall, I think my models are doing a good job all around. But like I said before, if we go to the final plot in this paper, we can see that the different mass components are all laid out here. Again, we have a log 10 of enclosed mass as a function of radius, and you can see that the stars are the dominant contributor of the total mass after a certain point. And the idea here is that when you don't have good constraints at the center of the galaxy, as in if you just have like an absence or a dearth of gas at the center here, then it's very hard to put precise measurements because essentially you have what is known as a degeneracy, as in you can have more stellar mass and lower black hole mass, and those will give sort of the same recreated observed data set. And so what you need fundamentally is you need to have high resolution observations that are tracing material, like gas material, down to the very centers of these disks and being able to resolve the complex motions of those gases within the black hole's sphere of influence. So you want to be able to isolate and look at the kinematics of gas that is mostly being affected by the black hole and not the stars, which is why you need very high resolution to do that, because if you look at close to the centers, and but also then you might notice things where that rotation isn't the only motional component of that gas's motion. So hopefully that made sense. But I have been talking a lot, but maybe it's because I have I did a lot of work on this, and I lived this experience. It took more than 3 years to get this all done. I will say one thing: when you're doing research, the final paper is not a true reflection of how much work was put into the actual research project. I mean, there's only like 6 models here. I ran like hundreds of dynamical models before I got to a point where I was like, these are the best, subset of those models that best recreate the observed data. And if I can just talk a little bit about sort of the experience of it and, the ups and the downs and what I came away from doing this. This is my first sort of end-to-end PhD level research project, and what it all felt like in the moment was just absolute confusion, honestly. I mean, I was so confused at many times during this project, and there was just times where I just had no idea that I could keep going, in the sense that I was stuck. There was times where I was like, how on earth am I going to be able to quantify the extinction from these color profiles? I don't have any idea how. At one point I was building the code that is in section 4, right? This whole code that I developed, there was moments where I didn't think I could do it. I mean, I had to start from almost nothing. I read these papers pretty much that had the predecessor version of my own code, and it was just such a relief when I was able to get it to work the first time, when I was able to actually to fit an ALMA data set with a previously measured black hole mass by my predecessor, actually. So that's, let me get to the section here. Yeah, so that's Boisel's work. Essentially, I pretty much took the results in this paper and I built my dynamical model to fit the data set, the ALMA data set that's in this paper, and my code got the same answer that was in this paper. So that was sort of the first confirmation that, wow, my code actually works. It actually, recreated a published known result. Now it can go off and, make its own published results, which the evidence is right here. All I can say is that when you're in those kinds of situations, just keep going and don't be afraid to ask questions. Ask a lot of questions. I was asking my advisor a ton of questions. I emailed Ben Boisel quite a lot about how do I do this? What does your code do? How would you go about addressing this issue? And you also just have to read a lot of papers. I mean, if you go down here to the references, these are a ton of papers that were part of the final solutions to some of these problems. I mean, just sort of getting the background knowledge and how to create these models, how to assess certain uncertainties. All around, it was just it was really like a baptism by fire, honestly. It was just sort of being thrown into the deep end of the pool and being like, I have no idea how to first of all, I didn't even know how to code in Python at that point. Sorry to my advisor if he thought I knew how to code in Python better, but I didn't. But I learned enough to actually make this paper possible. And all the figures you see here are by me. I plotted them all. All the software I built to make these is my own. And at the end of the day, I feel just better and more knowledgeable after this experience. Obviously, the measurements weren't the most precise ever, but I think the contribution to the field is that it really points out these degeneracies, which have been known, but I think that there are some works that just really don't go into the details of working out how much extinction there is at the center, using these color maps to work out how much light is lost and consequently how much stellar mass is lost or can be substituted for black hole mass. And I think I contributed something to the field, and that's all you can really hope for at the end. So I have been talking for a very long time, but I really hope you found this insightful. I hope you will read the paper. The link will be in the description below. I'm currently working on another one right now on top of writing my dissertation that will feature more of these kinds of measurements, and that will be a publicly available document when it's done. So hopefully that will be out in the next few months because I kind of need to graduate. But yeah, thanks for watching. It was great. It was fun to review this paper, remember everything I learned, and I hope it gives you some insight as to what a PhD student has to do to get their PhD. So anyways, until next time, I hope you have a great day.